Welcome to EC Chemistry channel. Today we are going to see about the basic concepts of aromaticity. Here we'll be talking about what are aromatic, anti-aromatic and non-aromatic compounds, how to identify aromatic compounds, and we'll be dealing with examples from benzenoid, non-benzenoid, heterocyclic and annulenes. Apart from this, we will also see how to identify aromatic compounds with NMR technique. Now let's see what is the criteria for aromaticity. Basically, the molecule has 4n plus 2 pi electrons. Otherwise, we can say the molecule will obey Huckel's rule. Next, the molecule will be cyclic. There will be a ring of atoms. The molecule is planar. That is, the molecule will lie in the same plane. The molecule is fully conjugated, and the delocalization of the pi electrons over the ring will result in lowering of electronic energy, and the molecules are highly stable. Now let's see what's Huckel's rule. In 1931, German chemist and physicist Erich Huckel proposed a theory to help to determine if a planar ring molecule would have aromatic properties. The rule states that if a cyclic planar molecule has 4n plus 2 pi electrons, it is considered aromatic. Based on Huckel's molecular orbital theory, if all the bonding molecular orbitals are filled with pair of electrons, the compound is stable. Benzene and Huckel's rule. When the compound is aromatic, 2 electrons first fill the lowest energy orbital, and after which 4 electrons fill the subsequent energy levels. In Huckel's rule, n denotes the energy levels, which is an integer. In benzene, we have 6 pi electrons, where the first 2 electrons fill the lowest energy orbital, followed by the remaining 4 electrons in the succeeding energy levels. Thus, all the bonding orbitals in the benzenes are filled, leaving the antibonding orbitals. Now, let us move on to the criteria for antiaromatic compounds. Antiaromatic compounds are cyclic, they are conjugated, the molecules are flat or planar, the molecules will have 4n pi electrons. They will not obey Huckel's rule, and they will have only 4n pi electrons. Delocalization of pi electrons over the ring must result in increase in electronic energy. The molecule is unusually unstable. What is the criteria for non-aromatic compounds? The molecules need not be flat or cyclic. The molecule may not have conjugation. They need not obey Huckel's rule. They may or may not have pi electrons. Now let's go into the examples. Benzenoid aromatic compounds. Apart from benzene, we have some more benzenoid compounds which are aromatic. For example, naphthalene, a bicyclic compound, is aromatic. It is obeying Huckel's rule with 10 pi electrons. It is planar and it has conjugation. The tricyclic compounds like anthracene and phenanthrene, they are also cyclic. They obey Huckel's rule with 14 pi electrons. They are planar and are conjugated. These are examples of some benzenoid aromatic compounds. Is pyrene aromatic? Pyrene is having 4 benzene rings and it is cyclic. It is flat. Every atom in the ring structure of pyrene is sp2 hybridized. But the pyrene molecule fails with Huckel's rule. Here, the number of pi electrons is 16 and does not fit in 4n plus 2 pi electrons. Hence, we may think that it is not aromatic. But 4n plus 2 rule is generally applied to monocyclic systems. Here in pyrene, the monocyclic periphery has 14 pi electrons, and the double bond at the center does not take part in the resonance. Hence, the number of pi electrons becomes 14 and it is aromatic in nature. Benzenoid compounds, which are anti-aromatic. Let's see an example of a benzenoid compound which is anti-aromatic in nature. Even though it has a structure of benzene, the biphenyl, it has two benzene rings. In it, it is not aromatic. It does not obey Huckel's rule and has 12 pi electrons. Hence, it is anti-aromatic in nature, which is also planar. Aromaticity in heterocyclic compounds. In heterocyclic compounds, if the lone pair of electrons on the heteroatom are parallel to the ring, they participate in pi bond formation of the ring and contribute to the resonance. If the lone pair of electrons are perpendicular, they do not participate in aromaticity. Based on this, it is easy to identify which heterocyclic compounds are aromatic and which are anti-aromatic. Let us see an example of pyridine. In the bonding structure of pyridine, the nitrogen is sp2 hybridized with 2 of the 3 sp2 orbitals forming sigma overlaps with sp2 orbitals of neighboring carbon atoms, and the third nitrogen sp2 orbital contains a lone pair. This lone pair is perpendicular to the ring and does not contribute to resonance. The unhybridized p orbital contains single electron, which is part of the 6 pi electron system delocalized, and it takes part in the resonance. Hence, pyridine with 6 pi electrons is aromatic in nature. Let us see aromaticity in other heterocyclic compounds. In pyrimidine, we have 2 nitrogen atoms. Both the nitrogens contribute to pi bond, and the lone pairs are perpendicular to the ring and do not contribute to aromaticity. The molecule is planar and has delocalization with 6 pi electron, and it is aromatic. Furan, here the 2 lone pairs on the oxygen atom. There are 2 lone pairs on the oxygen atom, one of which is parallel and it is contributing to the resonance. The other is perpendicular and does not contribute to resonance. Therefore, it is aromatic. The same is the case with thiophene, where instead of oxygen we have sulfur, where the lone pair contributes to the pi bond, and it is aromatic in nature. In the case of pyrrole, we have lone pair on the nitrogen atom, which takes part in the delocalization as it is parallel to the ring, and the number of pi electrons becomes 6 and it becomes aromatic in nature. In the case of imidazole, there are 2 nitrogen. One of the nitrogen, the lone pair is parallel to the ring and it contributes to the resonance, whereas the other one is perpendicular and does not contribute to pi bonding, but it is aromatic in nature. Now let's see the aromaticity in annulenes. Annulenes are cyclic compounds. Let's take an example of a simple annulene, 4-annulene, which is otherwise 1,3-cyclobutadiene. It is planar, cyclic, conjugated, and it has 4 pi electron. It does not obey Huckel's rule and it is aromatic in nature. If we talk about 6-annulene, where we have otherwise it is benzene, we all know that it is having planar, cyclic, conjugated and 6 pi electrons, and it is aromatic in nature. 8-annulene, the other name is cyclooctatetraene. This has the cyclic structure, conjugated and 8 pi electrons. But it is not planar, but it is tub shaped. This regular planar octahedron has a bond angles of 135 degree with large bond angle strain due to large deviation from sp2 bond angles of 120. To overcome this strain, the molecule assumes a tub-shaped geometry and hence it is non-aromatic nature. Let's take aromaticity in 10 annulenes. 10 annulenes exist in 3 different isomeric structures. First one, all cis isomer. It is having a full convex decahen with bond angle of 144, which creates a large amount of angle strain, and it is unstable, and hence this structure is non-aromatic. In the all cis form adopts to a boat form to relieve some strain and loses its planarity, and it is non-aromatic in nature. In the trans-cis isomer suffers a steric repulsion between the two internal hydrogen, and it makes it non-planar. So it is non-aromatic in nature. So 10 annulene, even though it is cyclic, conjugated and obeys Huckel's rule, because of its non-planarity, it is not aromatic in nature. When the interacting hydrogens are replaced by a bridging methylene group, as shown in the figure 4, the system has 10 pi electrons, planarity and resonance, and it becomes aromatic in nature. Aromaticity in higher annulenes. 12 annulene, antiaromatic. 14 annulene, antiaromatic. 16 annulene, aromatic. 18 annulene, aromatic. The same rule applies for all these higher annulenes also. Aromaticity of cyclopentadienyl ions. Cyclopentadiene is cyclic, which has a sp3 hybridized carbon at the 5th position. There is no relocalization, and it is not planar. Hence it is non-aromatic in nature. Cyclopentadienyl cation. Removal of a hydride anion from cyclopentadiene results in cyclopentadienyl cation. Here the sp3 hybridized carbon is altered to sp2, and hence cyclic uninterrupted pi cloud is formed. The molecule is cyclic and it is planar, and hence it is antiaromatic. Cyclopentadienyl radical. Removal of hydrogen atom results in cyclopentadiene radical, which has sp2 hybridized carbon but with 5 electrons, and hence it is non-aromatic. Cyclopentadienyl anion. Abstraction of proton results in cyclopentadienyl anion, which has sp2 hybridized carbon with 6 pi electrons and uninterrupted pi cloud, resulting in the delocalization. Hence it is aromatic. To summarize, cyclopentadiene is non-aromatic. Cyclopentadienyl cation with 4 electrons is antiaromatic. Cyclopentadienyl radical with 5 pi electrons is non-aromatic. Cyclopentadienyl anion with 6 pi electrons is aromatic in nature. Aromaticity of cycloheptatrienyl ions. Cycloheptatriene has 6 pi electrons but not conjugated, and hence it is non-aromatic. Cycloheptatrienyl cation, otherwise called as tropylium ion, this has 6 pi electrons, conjugated, planar, and hence it is aromatic. Cycloheptatrienyl radical has 7 pi electrons, not conjugated, and hence not aromatic. Cycloheptatrienyl anion has 8 pi electrons, conjugated, highly unstable, and it is antiaromatic in nature. Aromaticity of cyclooctatetraene. Cyclooctatetraene is otherwise 8 annulene, which, as we have seen already, is antiaromatic in nature. Cyclooctatetraene dianion has 10 pi electrons, and it is planar and conjugated, and hence it is aromatic. Now, how to identify aromatic protons by NMR technique? In benzene, many other aromatic structures, a sextet of pi electrons is delocalized around the ring. When the molecule is exposed to magnetic field, these pi electrons begin to circulate in a ring current, generating their own induced magnetic field that opposes the magnetic field. In this case, however, the induced field of the pi electrons does not shield the benzylic protons from B naught. Rather, it causes the protons to experience a strong magnetic field in the direction of B naught. To understand how this happens, we need to understand the concept of diamagnetic anisotropy. The line of force in magnetic fields are actually anisotropic. They start in the north direction, then loop around like a snake biting its own tail. If you are outside the ring in the figure above, we feel a magnetic field pointing in northern direction. If you are inside the ring, however, we feel a field pointing to the south. Aromaticity and NMR. In the induced field generated by the aromatic ring current, the benzylic protons are outside the ring. This means that induced current in this region of space is oriented in the same direction as B naught. In total, the benzylic protons are subjected to three magnetic fields: the applied field and the induced field from the electrons pointing in one direction, and the induced field of the non-aromatic electrons pointing in the opposite direction. The end result is the benzylic protons, due to the anisotropy of the induced field generated by the ring current, appear to be highly de-sheeted. Their chemical shift is far downfield in the 6.5 to 8 ppm region. In the aromatic compounds like benzene, the protons on the aromatic ring are shifted downfield. For example, 6 protons in benzene are magnetically and chemically equivalent and appear at 7.33 ppm. This is further downfield than alkene protons, which appear between 4.5 to 6.5 ppm. Thus, NMR serves as a useful tool to determine whether the compound is aromatic. Now let's see the comparison of NMR of benzene and cyclooctatetraene. So in benzene, we see the peak around 7.5 or here 7.33, whereas in cyclooctatetraene, which is non-aromatic, we see the peak at 5.78. To summarize, 2 pi electron systems like cyclopropenyl cation is aromatic in nature. 4 pi electron systems like cyclobutadiene, cyclopropenyl anion, cyclopentadienyl cation, which does not obey Huckel's rule but cyclic, conjugated and planar or antiaromatic. 6 pi electron systems like benzene, cyclopentadienyl anion, cycloheptatrienyl cation, and heterocyclic compounds like pyridine, pyrrole and furan are aromatic. 8 pi electron systems like cyclooctatetraene, cycloheptatrienyl anion, cyclotetraenyl cation, pentylene are antiaromatic. 10 pi electron systems like naphthalene, azulene, indole, quinoline are aromatic in 12 pi electron systems such as 12 annulene, heptalene are cyclic, planar. The molecules are conjugated but they do not obey Huckel's rule. Hence, they are antiaromatic. Thank you.